Hello? We're trying to start. Can you hear us? No, it's muted. Because Alice estava. I'm gonna say again. I just welcome you, but I'll say it again. So you can speak because we couldn't hear you. All right. Let me, because I'm talking to you on the phone right now. Let me hang up, see if you can hear me, okay? All right, so I cannot hear anyone right now. Can you guys hear me? All right, so you can hear me, right? Right, so I don't know what's going on here because I could hear you, but suddenly everything is stopped. So hey Amelia. We heard you first second and now we are hearing you. Okay, so if I hang up, you can hear me, right, when I talk? Yes, I think we did. For a second, we heard it. Right now, again. Okay, all right. So I'm gonna start talking about it. So just call me if you couldn't hear me, all right? Okay. All right, sounds good. All right. So thank you so much, everyone, for giving me this opportunity to present my research on corn ash. My name is Mahmoud Shakouri. I'm an assistant professor at Colorado State University. Before joining CSU, I was working at University of Nebraska. And Nebraska is very famous for having a lot of corn. And that's where I got, introduced to, to this research and started building my lab based on corn ash. So currently, I'm also a faculty member in the School of Advanced Material Discovery and also director of the Cement and Concrete Research Lab. My research area is concrete durability, service life modeling, corrosion, and sustainable cementitious materials. So I'm very happy that I can present this research because this is something that I've been working on, I would say, since 2017. And most of the stuff that you see here is from my previous work at the University of Nebraska. All right, so in today's presentation, what I'm going to do is I'm going to talk about some of the challenges that are facing the cement and concrete industry nowadays, especially after the green movement. Everyone is talking about making concrete green. So we're going to look at some of the challenges and see how we can overcome some of those. One possible solution to overcome some of these challenges is to use crop residue ashes. This is mainly types of corn, and I'm going to show you how one of them failed and one of them worked. So a lot of you have probably heard on the news that concrete is ruining the environment, and there is a lot of carbon emission because of production of cement everywhere in the world. And that is, partially true. One thing that a lot of these news agencies don't cover is that concrete by itself is not a bad material. The problem that we have is that we make a lot of concrete. After water, concrete is the second most consumed material in the world. A lot of concrete is produced every year. China, India, United States. So because of the mass of production, we have a lot of problem with that. But it has to be remembered that concrete by itself, if you put concrete next to aluminum, aluminum is more, dangerous for the environment compared to concrete or cement. And one of the things that you need to notice when you look at these statistics in the news or on the research papers is two indexes are typically used to refer to the environmental impact of a product. One is embodied carbon, and one is carbon footprint. And these are pretty similar to each other. The difference is that embodied carbon is usually what we say cradle to gate. It covers the amount of carbon emission that is produced from the production up to the delivery. So the transportation is also included in that. On the other hand, carbon footprint refers to the total amount of CO2 or carbon emission throughout the service life of the product. So it's a cradle to grave or cradle to grave, cradle to cradle, carbon footprint. So once we know these two, it would be easier for us to compare different materials. Here is an image showing how different materials, the embodied energy, very similar to embodied carbon, differ from each other. And as you can see here, concrete is at the end of the list. So concrete by itself, we don't put too much energy for producing the material. As you can see, copper, aluminum, they're top on the list. The problem is we don't, if we produced as much as concrete that we produce, if we produce as much aluminum as we produce concrete, probably we would see that everyone would be complaining about aluminum. But because we are producing too much concrete and no other material can reach that extent, that's the big issue that we have to resolve. To just give you a perspective, what's going on at least in the United States, this is kind of like all the statistics, but kind of the trend is still the same. So we are kind of increasing our production of cement in the United States. And at the same time, we're consuming more cement. So there is a gap between the demand and supply. So the United States also imports some cement to fill that gap. And countries like India, China, they are mass producers of cement. One statistic that you'll typically see in the news or in the research paper is that for every pound or every kilogram of cement, about 85 to 90% of it is CO2. So same amount, almost 1 to 1, the ratio 1 to 0.9 or 1 to 0.85, you're producing CO2. And that's not really good because if we were not producing that much cement, nothing would happen. But since we're producing a lot of cement, 120 million is a big figure. So imagine you're releasing 80% of that number as CO2 in the atmosphere every year. On the other hand, one of the materials that we use a lot in the United States to kind of offset the negative impacts of cement is fly ash. And fly ash production is going down, and this is basically the byproduct of burning coal in the coal-based power plants to produce electricity. So it's a very useful material. We typically include 10 to 20 or maybe 30% of cement, replace that with fly ash. Fly ash has a less environmental impact because it's a waste material that we get from a different process. But the issue in the past, that, and it's continuing right now, it's a critical issue in most states in the United States, is that a lot of these power plants are shutting down, and they're not producing as much fly ash as they used to. So a lot of concrete producers are trying to find a replacement for fly ash. And that's been the consumption rate of fly ash has been constant throughout the years. So we have the same amount of consumption, but our production goes down. So that creates a very big challenge, at least in the United States. Now, to offset some of the environmental impact of not just concrete, but the construction industry itself, in the United States, every state is taking the lead to produce some programs or introduce some programs to kind of limit the amount of CO2 that is produced by producing different materials. For example, in Colorado, where we are, this Buy Clean Colorado Act was passed in 2021, and every project that works on the federal money, like state money, they have to reduce their gas emissions by at least 10%. So what they're trying to do is they try to make, for example, concrete producers to show that they're doing something to reduce their environmental impact by 10%. And that can include reducing the cement paste content. It can be adding different type of supplementary cementitious material or different types of cement that has a lower environmental impact. So there are a lot of programs like this nowadays in the United States. Just show you a few of these, but I can see that in the future most states have something similar, and that kind of limit the amount of CO2 emissions that are produced by the concrete and cement producers. The Portland Cement Association, this is a big organization that basically controls the production of cement in the United States. They have a plan, they have a roadmap to reach carbon neutrality by 2050. What it means is for the same amount of CO2 that you produce, you have to be able to capture that amount by using different techniques, or either you can do it during the clinkering production process by using different types of fuels, or using different types of cement, adding supplementary cementitious materials, designing your concrete in a better way that it requires less cement paste, or by designing your structure that is doesn't require that much concrete. So you don't have to design a column to be very bulky if you can do it with a smaller size. And at the end, concrete is a carbon sink. What it means is over time it captures this CO2 from the environment. So basically it's a good thing. And what this PCA is proposing is, we have to optimize this production and design and service life, maintenance part, so that at the end of the service life of the concrete, the amount of CO2 that is produced equals to the amount that has been captured. Now, a lot of research nowadays is focused on the cement part, the binder, and each research group is looking at different type of material. So you'll see that every day a new material pops out that if you add this material, you can reduce the cement CO2 production by X amount of percent. So again, this has been exacerbated because of the shutdown of the power plants. So a lot of power plants right now in the United States are either closing down or shifting from coal to other types of resources like gas, and that creates one big problem because you don't have fly ash to replace in your cement. So nowadays, a lot of state DOTs are looking at using slag. Slag is another byproduct of the steel industry, but the slag is more expensive and it has different properties than fly ash when you add it to your concrete. So a lot of research is going on. One possible solution for this limited amount of fly ash that we are producing is to look at the local materials that we have Every city, every state, every country, they have some local materials that they can use to create a sort of a cementitious material. And this ternary diagram basically shows what is the main composition of some of the main common materials that we use in the concrete or in cement. Silica, calcium oxide, and alumina is the main thing that we look at. Not that other physical properties are not important, but first we look at the chemical properties and then we look at the physical properties. But a lot of these corn or rice or wheat or any type of agricultural residue products, they have a decent amount of silica, and they can be used for basically as a replacement for cement. Now, one of the things that we have to make sure that, and one of the questions that I usually get is, what's the application of this residue? Are we competing with other activities? For example, sometimes the farmers, when they harvest, I don't know, let's say wheat or corn, they may use that residue as a cattle feed. So you're competing with the cattle feed because that's the useful material that they feed to cows or sheep. Sometimes farmers just leave these residue on the farm, or they burn it to act like a fertilizer. So when you are considering using a residual as a supplementary cementitious material, there has to be some sort of a cost analysis to see what's the benefit and what are the disadvantages. And when it comes to commercialization, companies that want to invest in your product, they always ask, is it reasonable to kind of get the product from the farmers and put more energy into it, and then convert it to something that concrete producers can use. So everything has to be analyzed before making a new product, because if it's not really cost effective, it's not really reasonable to do that. You can have the best material, but nobody's gonna produce it or buy it. All right, so let's talk about these crop residual in more detail. So a lot of research has been done, and there are a lot of research ongoing, and they'll look at different materials. One of the things that most of these research have found is that when you add these materials in form of ash into your concrete, they show pozzolanic reactivity. And what it means is that during the cement hydration, when you add cement and water, it hydrates. And we have a component where we have a calcium hydroxide that is produced. And this calcium hydroxide can be consumed by these ashes, these residual ashes, and they can produce calcium silicate hydrate, which is the building block of concrete. Calcium silicate hydrate is what gives concrete its strength. So when you can consume that calcium hydroxide to produce that calcium silicate hydrate, this is a good thing for concrete because you would have a denser and a stronger concrete. So a lot of materials that like rice, wheat, sugar baggage, and all of these have been shown that they show pozzolanic reactivity. And things that we can see their effect in concrete is like they in most cases they change the matrix of the concrete. For example, water or harmful species, they cannot penetrate into concrete because the concrete becomes denser. These are all different types that we can see. There are more. I'm sure every country has some sort of a local or indigenous plant that they can use for producing these type of ashes. Most of these products, they are leafy products. They have cellulose, and when you burn these, you have a very fine ash that typically ranging from starting from 40 to up to 80% or is made of silica. So why corn is important and why I studied corn is because United States is the largest corn producing country in the world. So we produce the the most amount of corn in the world. We put corn in everything, in milk, in formulas, in our, I don't know, drinks. So we need corn, and corn is used also to make ethanol for, for cars. So we have a lot of corn, and I'm sure Brazil is very similar. Brazil, I think, is the third largest country after China that produces corn. So the magnitude is very important because you're looking for something, you're using a product that is very sustainable, and you're producing corn every year, so you have a lot of it, and you can produce a lot of ashes with the waste part. So that's one of the main reasons that corn is much better than other types of residual. Wheat is also possible, but not every country produces wheat. Rice is good, but rice is, again, a lot of environmental requirements are needed for growing rice, so they cannot be grown everywhere. So corn is, I would say, is #1 option that can be used for this purpose. So what are the benefits of using these residual ashes in general? Well, first is environmental benefit. You're producing a material that is a waste. So all of these residues are considered to be a waste. And when you convert them to ashes to be used in cement, they typically require less energy to be in the form of ashes. So you are putting less energy to get the same type of material that we can use for cement. Economic benefits, you are creating more avenue for farmers or for people to basically produce these materials. So it creates jobs for the communities. So that's a good thing. And in terms of technical benefits, a lot of these materials can be used to enhance the properties of concrete. And that's what we're looking for. We don't want to add something into concrete that makes our concrete weaker. We want it to be stronger. So a lot of these products can do that. Now, just to give you an idea how much environmental impact we can offset by producing corn ash is, like, if you have an acre of cornfield, okay, you can generally harvest about 7 tons of dry mass corn stover. And corn stover is the term we use to refer to corn stalks and corn leaves, the plant itself, not the seeds. So if you compare producing corn, the heat value, basically the amount of energy that you can produce by burning these corn stover, is not that bad, compared to coal. You get almost about 70% of the same heat value, which tells you that these corn stover can be used as a source of energy for producing heat. So they can be fed into the kiln when you are making or producing your cement. So they generate heat. So that's a good thing. The other thing is that their CO2 emission is almost, let's say, 10% of the coal. So there you go. You can reduce your CO2 emission by 90%, which is far more greater than what the typical programs the United States are requiring. So they typically want 10%. You can reduce that by 90% by replacing part of your cement with corn stover ash. So on average in the United States, okay, about 6.3 million metric tons of corn stover can be produced. Okay, so if you get only half of these stover and convert it to ash, you can offset about 7% of cement production, which basically is a huge value. You can reduce the CO2 emission by about 4.5 million metric ton per year. So that's the huge value if you want to change the environment. So there is some science behind it. There is some motivation behind it. Corn ash can reduce the environmental impact. So why not give it a try and see how it works? So there are a couple of challenges with any of these materials. The first challenge is the variability. Even when we are getting corn from different farms within the same city in the United States, we can see that and their chemical properties are different. So that creates some issues. So there has to be some sort of a quality control and quality assurance program in place to make sure that when you're producing these ashes, you are not really deviating from the main properties or main chemical composition that you're looking for. Right now, we don't have any standard testing for these type of materials. No ASTM testing is there for plant-based ashes. So we typically use ASTM that is applied to fly ash or slag, and try to come up with the numbers to show that these products are working. But there is a very important significant need for making some testing, standard testing for these materials. And then the potential, there is a potential for increased cost because a lot of us researchers, we create these materials in the lab, and in the lab everything is more expensive than if you have a mass production. So there has to be some cost analysis to make sure that it's beneficial. What we came out when we analyzed our products was that we can produce these a little bit more than that $100 per ton, which is kind of more expensive than cement. Here in the United States, you can buy cement for $40-50 per ton. So that's something that when you don't have fly ash, you have to decide. You have to decide if you want to go with something that is a little bit more expensive, or if you want to make a inferior concrete without any SCM. So these are the things that has to be decided before committing to producing these materials. All right. So the way that these materials are produced, and I think this is one of the sources of variability, is that they are typically burned in an open burning process. Basically, you have a barrel or a container, you put these materials in it, and then you burn it. And then some researchers, they process it before burning. Some researchers process it after burning to remove some of the impurities. I'm going to look at this processing part in my second case study to see how it will affect the properties of your ashes. And then different researchers, they use different materials, they use different contents. So some add 5%, some add 10%, some add 20%. So these are the things that kind of create some variability when you compare different studies. Not everything is the same. So it's very hard to compare one study with another. And that goes to my first point on lack of a standard testing. We need to have some standardization for these materials so that everyone produces the same way, and then we can test them and compare the result the same way. All right, so I'm going to focus on case studies. I think I have about 15 minutes, so let's cover these case studies. The first case studies that I have here is looking at the properties of concrete made with corn cob ash. So corn cob is the part that holds the seed, and so I did not include any leaf or stalks in this part. So a lot of researchers, especially in African countries, have done a lot of research on these corn cobs. So we started with this. This was the first experiment that we conducted to see if using corn cob ash is beneficial in concrete. And these are some of the previous studies that have been done. There are countries from some Asian countries and some African countries. But in general, most of these studies show that your concrete strength by using corn cob ash goes down. Some studies, they have contradictory results in terms of workability. Some said that the workability goes up, so it improves. Some said, no, it goes down. Unit weight, everyone, I think it should go down because you're replacing your cement with something that has a lower density, so your unit weight goes down. And there are some mixed results about water absorption and sulfur resistance. Now, in terms of production process, most research, I would say all of the researches that I found, they use open burning method, basically no control over the temperature, no control over the amount of oxygen. They use different temperatures for burning from 400 to 800 Celsius. Some researchers, they did post-processing. The grinding method plays a very important role in the final properties of our ash. A lot of researchers, they use ball mill, so they mill it in ball with small, heavy ceramic or metal balls inside a jar for different durations from 30 minutes to 60 minutes. And depending on how long you're doing the grinding, you would have different fineness. So we should try to have a fineness that is similar to the fineness of cement. Okay, so you don't want to go too low because it would have severe impacts on your water demand and workability. So what we did was basically we got some corn cobs from the farms. We had this cyclonic ash burner. It's a unique feature because it has a fan on the top that kind of creates a cyclone inside the barrel, and when you start the fire, it basically gives more air to fire to burn. So you would have a faster burning rate. So when you get the material out of this, it has a lot of carbon. So it's the ash is black. That means that it has a lot of carbon, and you don't want to have carbon in your cement because it kind of has a negative impact on your properties. So what we did was basically we had a post-treatment, second heat post-treatment at about 600 degrees to kind of burn that extra carbon in the ash. And after that, we had a milling machine that we used that for grinding the ashes. So we did our milling time was about 30 minutes to 40 minutes. And this picture shows the pictures taken at each step showing the final products that we had. So the color is kind of grayish color, and that shows that there is still some carbon in it. Okay, if you want to burn all of that carbon, you have to put a lot of energy into it. So that makes it a little bit less economical. And basically you're consuming more energy so that you're producing more CO2. That's the thing that you should avoid. So we were happy with this. So we used this and we did a series of experiments to find out what are the physical properties, what are the chemical and mechanical properties of concrete made with this corncob ash. So we look at particle size distribution, chemical composition, the crystalline phases, morphology, the hydration process, the reactivity, compressive strengths, see how it reacts to the diffusion of water and chlorides, and also look at the pore solution chemistry, because pore solution chemistry basically defines the pH of your concrete, and if your pH is down, that's not really good for reinforced concrete because it may promote corrosion. So we got our chemical composition results, and one of the things that we first noticed initially was that we didn't get that much silica. Our silica was about 20%, but that was not really concerning. The concerning part was the amount of potassium that we had in the ash. We had almost about 40% potassium, 38.1% potassium, which tells us that they're probably they used a lot of fertilizers to grow those corn, because potassium comes from fertilizer. So we compared that with what other researchers have reported, and there were some similar studies that they had high potassium, and there were some studies that they had low potassium. So we kind of searched about it to see what's going on here, and we found out that in some countries, like African countries, because they don't have that much water, they just plant the corn and they let the environment take care of it. So they don't add any fertilizer, or they don't add any liquid fertilizer to the corn. So we thought probably that's the main reason some of these ashes, they had a lower potassium content. But for example, the 31% was pretty close to what we had. So it's a concerning issue. So you should not use an ash with that amount of potassium or sodium because it will affect the properties of your concrete. What we have here is a particle size distribution on the left, and it's kind of very similar to what we see for the cement. And on the right is the crystalline phases. And this S that you see here, the two tall peaks on the right side, these are for sylvite, and sylvite is potassium chloride. So the corn cob that we tested had a lot of potassium and it had some chlorine. And when you burn that, you're producing that sylvite. So sylvite causes a couple of issues. First of all, it affects your hydration. Also, when you burn it, when you burn the corn cob, things like to agglomerate. They become stiff, and you will have, instead of having a ash, you have a chunk of ash stick together. So that's kind of problem that we saw, and that's the reason that's because of the sylvite. In terms of particle size morphology, they are not really rounded shapes. They have these, weird shape that it can create a couple of problems. First of all, when you have shapes that are angular, it causes, it increases your water demand for your mix. So what it does to your concrete, it makes your concrete less workable. All right, so you're adding this into your concrete becomes stiffer, and that's one of the issues that this is the issue for all types of residues. In terms of hydration, we saw that the heat of hydration that we produced by incorporating these two ashes, they were lower than the normal cement. Okay, so on the right side, this left and right picture, they're kind of similar. The right one, we typically look at the right one, which is the cumulative heat release. The red dotted line is the normal OPC, and then the black one is your fly ash. So when you compare your corn cob ash with fly ash, it's kind of similar, but it has a lower heat of hydration at the initial stages. So what it means is that it takes more time for your concrete to reach that stiffness or that hardness. It depends. Sometimes it's a good thing, sometimes it's not a bad thing. It depends on your temperature and your application. But showing that these two are lower, both of them are lower than OPC, means that they are less reactive. Basically, it takes some time for them to kick in because of the pozzolanic reaction that we have. So first we need to produce calcium hydroxide, and then those ashes can use these two materials. And then we had the reactivity of tested reactivity of these ashes. Basically, you can see the calcium and the CCA, which is the corn cob ash, is not really a reactive material. It's kind of similar to quartz and a very inert material. So we found out the reason behind that was that first of all, we had too much potassium, and then we didn't have that much silica, and probably the silica was not that much amorphous. So that really did your chemical process that happens during your hydration. In terms of compressive strength, we saw that if you compare the first three columns with the second and third group, you'll see that in general we got less compressive strength, and that's really that was expected because we were adding an ash that is not as reactive as the Portland cement itself. So what we did basically measured the strength at different ages, and we saw that even after different ages, the strength did not improve, showing that the ash was not really reactive. On the right side, we have a result of a test. This is basically a rapid chloride permeability test. The lower the value on the y-axis is, the better. So you don't want too much charges to pass your concrete. Basically, you have a concrete, you put it into two cells. One cell is chloride, one cell is sodium hydroxide, and you apply voltage, and you just see how many coulombs or charges passes. The higher the passage, the more permeable your concrete. And as you can see, if you add 20% corn cob ash, you're drastically increasing your permeability, which is not a good thing. In terms of resistivity, again, we kind of saw the same trend. The resistivity went down, meaning that your concrete is more permeable. So that's not really a good thing. And then in terms of ionic concentration in your concrete, we can see that, in the concrete, we had a lot of potassium, which is explaining why we see all of these results. We didn't get good strength, we didn't get good permeability. So at the end of the day, we found out using just the corn cob by itself is not really a good way to do it. We have to do something. One way to fix this problem is to pre-treat it. But we didn't want to just pre-treat the corn cob. So for the second phase of the study, we look at other parts of the corn plant, which is the corn stover. So corn stover is basically, it can include corn cob, but it mostly includes the corn stalk and corn leaves. One step that is added to this part is that the pre-treatment. We did pre-treatment with water and acid. So we had the corn, we washed it, we soaked it in water, and then we soaked it in acid. We used nitric acid for that purpose. So that was a 2-week process. After that, we dried it and we burned it, and then we post-treated with heat to reduce the carbon content, and then we ground it to make the ash. And this is a couple of pictures they took from me while I was doing it. And the picture on the right, that's the cyclonic ash burner that we had in the lab for producing the ash. So what we saw was totally different from the corn cob. The figure on the left shows the chemical composition. It's just a radial plot. And as you can see, for example, the acid-treated ash, which is represented by the green color, it has about more than 80% silica, all right? And if you look at the CO2, the potassium content is less than 5%. So from 30% in corn cob, we went down all the way lower than 5%, which was a huge improvement. Also, if you look at the red color is your water-treated corn stover ash. It has lower potassium, but is not as low as acid-treated. It also has lower silica content. So it's kind of something between untreated and acid-treated. So if cost is an issue with water treatment, you can basically do the same thing, but the quality is a little bit less better. On the right, we see the LOI, the loss on ignition. Basically, this is the percentage of your ash that you lose if you heat it up to 700 degrees. As you can see, with acid treatment, your LOI is pretty low because your acid will get rid of all those impurities in your ash. So you don't have anything to burn. It's all silica, and silica does not really burn. Now, we did, again, phase analysis to see what are the crystalline phases. The one at the bottom, you can see that the letter S around 30 degrees, you see there is an S, that's sylvite that we had, KCl, but you don't see that in acid or water pre-treated samples. That tells us that even water is very useful for removing all of those alkali contents in your ashes. In terms of amorphous content, they were all very similar with water, cement, water pre-treated was a little bit higher. One thing you need to notice that having more amorphous content is better in your ash because it makes it more reactive. So you want to have a little bit more amorphous content, but about 45%, 50% is very good number for these type of ashes. We saw the same type of shape and typology of the ashes. They are very sharp edge, angular. Again, we saw that this is gonna make our concrete require more water, and we saw it in the mixes as well. This is the particle size distribution. You can see by pre-treating the ashes, you can make it a little bit finer. So all of these 3 ashes were milled for the same amount of time, but you can see that the water and acid, because they had less impurities, they became finer. Surface area is again another factor that contributes to your water demand. The lower the surface area, the higher the lower the water demand. So you can see that acid and water, they had a higher surface demand, and this is kind of because of the particle size distribution as well. You know, if you have a finer particle, you have more surface area. But again, these all show that, you know, in terms of basically workability, all of these ashes reduce your workability. The density that we measured was about 1.3. Your cement density is about 3.15. So if you add this to your cement in your concrete, you expect to have a lower density concrete. For heat of hydration, we saw that using corn stover is a little bit better compared to corn cob. The cumulative heat is still lower than the normal concrete, but it was not as drastic as we had in corn cob. So for calcium hydroxide consumption, this is a metric that we use to kind of show reactive is the ash. The more we have consumption, the less the better the better your ash. So you want your ash to consume more calcium hydroxide. And you can see that both treated ashes, they had higher consumption than the untreated one. And then we did a modified R3 test. This is a test we typically use to see how reactive it is. So we mix our ash with potassium hydroxide and calcium hydroxide, and then we use a calorimeter, and then we use thermal analysis to determine how much calcium hydroxide is produced. And as you can see, our corn ashes, they are very similar in terms of reactivity in the same region as fly ash. So this is a very good finding that we found, that these ashes, then they can be a really good replacement for fly ash. In terms of strength, you can see that in this case, when we used corn stover, the blue color is your normal OPC. On the left side, we had 5% addition. On the right side, we had 20% addition. We saw that on the left side, if you had 5% addition, your strength will be higher than OPC. So that's a good sign. If you add 20%, initially your strength is lower, but over time you will reach the same strength as OPC. So these are basically telling you that, you know, these are good material for long-term performances. And then we had resistivity, which is a measure of durability. The higher the resistivity, the better. And you can see that our concrete had a very high resistivity when it was made with acid or water pre-treated corn stover ash, almost 2 times or 3 times more than normal concrete. So this shows that they can be more durable than the normal concrete. So what we found in the end was that pre-treating was good for corn stover. It helps us to reduce the potassium content and increase the silica content. Acid is much better than water, but again, both of them had very kind of comparable results. So if cost is important for you, probably you want to go with water. Things that I think is required for future research is, first of all, we need to look at the standardized testing. This is essential. Without a standardized testing, every person, every researcher is doing something different, and, you know, it makes it very difficult to compare the results. In terms of long-term performance, there hasn't been any study on looking at the performance of these concrete over, for example, 10 years or 5 years. So everything is short-term. So we need to have some long-term studies to look at these performances. Another thing that we have to explore is see how would the concrete behave if we have a ternary blend instead of having a binary blend. So what would happen if we mix, for example, corn ash with fly ash and cement, or corn ash, slag, and cement? So these are, again, things that I consider they need to be investigated. And finally, I haven't seen any study looking at the life cycle analysis of these products. I think it's very useful for people to know how the concrete made with these ashes have a different, carbon footprint over the service life of these structures. All right, with that being said, that was the end of my presentation. I have a class I need to run to, so if there are questions, I can answer maybe one question, but I cannot hear anyone. All right, Emily, is there any questions? I have a class I need to go.